All right. Hello. So this week we begin our discussion of lecture series number 6, which is essentially centered around the so-called von Neumann architecture, von Neumann model. It should be a relatively small lecture series because it turns out that subsequent or follow-up lecture series provide a more in-depth discussion of the various components that comprise the so-called von Neumann architecture. So in lecture series number 6, we essentially just gloss over those various components to set the stage. And essentially, what you're doing, if you've been following through with our previous lecture series, is we're essentially abstracting, right? And as we progress in our discussion of ICT 1110, we get to focus more on the specific details associated with the various components that comprise the von Neumann architecture. All right, so I'm just going to skip these slides because they were essentially included into these notes to walk us through quiz number 4. But there is a dedicated screencast that's centered around this. If you haven't watched it, I highly encourage you to go through that screencast. So I explain all these different numbers associated with the statistics linked to quiz number 4. But perhaps a slide that I did not include in the screencast centered around quiz number 4 is the so-called leaderboard. So one of the reasons why we normally include people that perform relatively well in class is so that you can easily reach out to them to ask for help if you need help, right? I think I probably mentioned in one of my emails that the people that continuously perform better than the others obviously doing something right. So probably want to reach out to them to find out what the secret is. All right. And by the way, great work to these guys here, right? Okay, so our lecture series is essentially going to walk us through these items here. And then we decided to break it up into two main parts. So first of all, set the stage by having a very brief introduction and then discuss the so-called stored program concept, which is the underlying idea behind the so-called von Neumann model, von Neumann architecture. Again, most of these ideas, including the von Neumann architecture itself, they're simple ideas but tremendously powerful, right? They're the very basis for most of these devices that we found ourselves using. These devices were computer systems. All right, again, repetition is a mother of skill here. Just a reminder that what we're discussing is centered around this thing we're discussing called computer systems is centered around this notion of an electronic device that does three key things. It accepts input, which is generally data, processes the data, right, transforms it, then produces obviously some sort of information, right? That information is presented to an end user in the form of output and optionally stored on persistent storage, right? So key things associated with this computer system. And again, the input is obviously the one that sets the stage for that interactivity that happens between an end user and the computer, because fundamentally what we're doing when we're using when we're working with a computer is we are telling the hardware what to do, but the actions that would want the way we convey that message, the instruction, is not direct, right? So we pass through so-called computer software, and so the computer software is the one that mediates between end users, which are sometimes human beings, and the hardware itself, right? And then the output obviously just provides a mechanism to gain access to the the result of the processing that the hardware does, right? So you submit data to the computer. That data could be in the form of text, sound, as is the case right now when I'm speaking through this microphone. It could be an image, it could be video, and then the computer will do a bit of processing, right? And the processing itself, right, is done by the hardware and the software. So it's not just the hardware in isolation. So both the hardware and the software sort of like collaborate with each other to process that data and then produce the output. And then obviously the optional storage of the output is facilitated by so-called memory components or computer memory, right? And again, we have lengthy discussions that are centered around different types of memory components, right? Specifically, I guess there's two broad categories: is primary memory and secondary memory, or secondary storage, as it's commonly referred to, or computer storage sometimes. All right. Again, in terms of these so-called physical hardware associated with the computer, again, just to try and wrap it in, that these are essentially just the tangible components, things that we can literally see with our own eyes and to a certain extent touch, right? And by the way, the reason we are more or less like talking about this again is so we don't lose track of what we are doing, right? It turns out that there's a golden thread that we are following through here, right? All these different things that we've been discussing up to this point in time are connected, and this is meant to be a reminder to us on some of these underlying concepts of a computer system, right? So the tangible components are obviously directed to perform some action by computer software, right? Which we've discovered comes in various forms, right? But fundamentally, it's essentially just two broad categories: application software and system software. And the type of computer software that specifically directs the hardware is usually manifests itself in the form of operating system software, right? Or it could be firmware in certain instances, like for single function devices, like embedded systems, for instance. Right. Again, essentially what's happening behind the scenes here is you have computer software directing the hardware, right, to perform a specific function. Of course, what you have is a sort of situation where you have an end user here, right? So there's another added component here, which is usually an end user, right? It could be like a human being or something. We've been good at sticky figures, but could be a human being who is here. But again, this whole notion of an end user is usually generic, right? Because there are certain instances where the end user that would be consuming the output of the processing could be another computer hardware. Another computer system rather, right? Or something other than a human being. So whenever we make reference to an end user, we try to leave that definition to be so open-ended that it encompasses much more than a human being. But we do know that for the most part, this actor we call the end user is usually a human being, right? Okay. But it turns out really that irrespective of how you look at these computer systems, irrespective of whether you are making reference to embedded computer systems, microcomputer systems, mini computers, server computers, mainframes, supercomputers, all those different subcategories that we discussed during our discussion of lecture series number 3, I think, it turns out that the underlying model that is used to build those computers is the same, right? And for most modern day computers, not all of them, but most of them, a huge chunk of them actually, they are based on the so-called von Neumann model, right? And this is a model that has been around for a couple of decades now, but it's so tremendously powerful that it's still being used even modern day computer systems, right? So irrespective of what that computer system is aimed at doing, irrespective of the complexity associated with its capabilities, its computational power, the underlying design that was used as a basis to build that particular piece of hardware or computer system is generally the von Neumann model, right? And I mean, granted, there are other models out there, And the classic one that is normally compared with the von Neumann model is the so-called the Harvard architecture, right? But fundamentally, the vast majority of computers are based on this model. So essentially, this is what we are going to look at, or partially what we're going to look at in this lecture series. This is what we're going to look at, actually. All right. And so it turns out that the fundamental idea that is linked or that is instrumental to the von Neumann model is this whole notion of the stored program concept. Now, before I proceed, there's a reference at the end to this really interesting report. It's an old report which was authored in 1945, right? So we can actually trace the roots of the so-called von Neumann architecture to as far back as 1945. So it's a first draft of a report on the EDVAC. I do encourage you to go through it. It was authored by John von Neumann, right? So the person who is considered the father of this architecture itself. You probably want to go through this so that you can try and understand a bit more about what this whole idea is all about. Now, granted, there's likely some aspects of the report that you might not be able to understand, but you should be able to make sense out of the first couple of pages of the report. I do encourage you to go through this. But in summary, really, this whole notion of the stored program concept is quite simple, really. The idea is that you typically have a hardware platform, right? A generic hardware platform that you use to execute a fixed set of instructions. So you have this generic set of instructions that is used to perform, or that is used to direct a piece of hardware, a fixed piece of hardware, to perform specified instructions or desired instructions. And the idea behind this fixed set of instructions is that combining them together results in these different operations that we can perform on a computer system, right? So one way of thinking about these fixed set of instructions are essentially just, you can think of these as being program codes, which when combined together will form these building blocks that perform operations. This will be simple operations like adding, for instance, right? Subtracting, multiplying, right? And it turns out, right, interestingly enough, once you combine these operations together, you come up with what we refer to as software or programs, right? So more complex functionalities or features that a computer is able to do. So an example program would be a program that would be able to render something onto the screen, for instance, right? Very simple, right? But again, if you notice, you're tracing a couple of interesting concepts here. Fixed set of hardware, right? It's a generic piece of hardware which is used in conjunction with a fixed set of instructions. And you get an appreciation of this whole notion of a fixed set of instructions once we start our discussion of the MIPS instruction set architecture. What you will realize is there's a fixed set of instructions really associated with the MIPS instruction set architecture. Less than 200 last time I checked. But when combined together, all those different instructions will result into these complex programs that we find ourselves using on modern day computer systems, right? The other thing is that the program instructions and the data that these program instructions will act on are typically stored in one location, which is the memory component, right? Remember, if we go back to our definition of a computer system, we are saying it's an electronic device that will essentially accept input, right? Process the input and then store the input. So the input is what we're referring to as data, right? You provide input to this computer system, and then the processing is done by the hardware in conjunction with software, right? If you remember, software is, it's one of the similar, it's the same thing as programs, right? Software are actually computer programs. So both the hardware, both the data that is provided, fed to the computer system or imputed to a computer system in the form of input, and the programs that act on the data are stored in one location, which is memory, right? And of course, the behavior, because you have a fixed set of instructions acting on this fixed hardware, the behavior of this hardware is dictated by the program that is currently loaded in memory, right? So the program that you're executing at that point in time. You could think of this as, if I was to use the current example, currently I have this application called Ocular that I'm using to go through these slides, right? To render these slides, these presentation slides. This is the application I'm using. So at this point in time, of course, there are other programs here, but you could view my computer system as being loaded with Ocular, right? So Ocular is currently loaded into memory, and what Ocular is doing is Ocular is is processing data associated with the slides that I've created. The slides are here, right? I've just opened this slide here. So this would be data, right? I've loaded another piece of data into memory, right? So Ocular is in memory right now together with the data itself. And interesting thing about Ocular here is if you go to just to try and emphasize this whole notion of memory, programs, and data, right? If I go to settings associated with Ocular and I try and specify exactly how I want Ocular to behave insofar as memory is concerned, you notice I have options like greedy options or aggressive or normal. The aggressive option that I normally go for tells me that everything is going to be swallowed into memory. So everything, the entire application and the data that the application is working on is going to be stored in memory, right, in RAM. And I can manage to get away with this because I have sufficient RAM, right? I have 12 gigabytes of RAM, so I can get away with that. But in the event that you have an application that has relatively smaller RAM in comparison to what I have right now, maybe you'd go for this option where so that you use up as less RAM as you can possibly use up. But anyways, I digress. The key things associated with the stored program concept here are very important things: fixed set of hardware, or a hardware platform, a generic hardware platform with a corresponding fixed set of instructions. The fixed set of instructions form the basis for building or coming up with these building blocks that we call operations. The operations will eventually result into the thing that you call a computer program. With that computer program, you can manipulate data that you impute to a computer system. As you are working with the program, as the program is manipulating or transforming, processing the data, both the data and the program will be stored in memory, right? And obviously the behavior of this generic piece of hardware is dependent on which program you have stored in memory. If I switch and I open Chrome, for instance, the behavior of my hardware will be dependent on the currently loaded program in memory. In this case, it's Chrome. Although, I mean, we are simplifying this because both Chrome and Ocular are actually loaded into memory at this point in time, right? Yeah. But currently, Chrome is loaded into memory, and the behavior of my computer will be based on the program that is currently executing in memory, which is Chrome, right? Very simple concept, but extremely powerful at the same time. All right. But the key concepts, again, so that's a stored program concept, right? The ideas behind the von Neumann architecture here is similar to the stored program concept here, just more or less like piggybacking on what we already talked about. Data instructions are stored on a single memory component, right? In this case, you could think of that single memory component as being RAM, right? So this could be RAM, for instance, right? RAM. This should be your RAM, okay? Of course, I mean, this could also be your secondary storage, actually, because it turns out that both the program instructions that I'm using right now, which is Ocular, both ocular and the data that I'm manipulating, which is this slide, are actually stored on a memory component, on a single memory component. In this case, the single memory component is obviously secondary storage, it's a hard disk or hard drive, right? But ideally, for the most part, the single memory component that you'll be referring to here is the RAM or primary memory, right? The other key concept associated with the von Neumann architecture is that these data and instructions, once in memory, are referenced by making use of unique addresses associated to their locations in memory. So you typically have a unique memory address that you associate to the data and instructions once they're in memory, right? So we're saying right now that ocular is loaded into memory. For us to be able to, for a computer system, in this case a central processing unit, to be able to make reference to ocular, or to the program instructions associated with ocular and the data that ocular is currently manipulating, it makes use of these unique locations we are calling memory addresses, right? And then, more importantly, the execution. Because for you to tell this fixed hardware what to do, you need to execute a combination of the fixed set of instructions, depending on what you are using the application for. So depending on whether I've clicked the feature associated with this file menu item or view or tools menu item, right, the behavior will be different, or the combination of instructions that will be used will be different. But the execution of those instructions is done in a sequential manner. So it's one instruction at a time. And it turns out that the execution follows a so-called CPU cycle, which involves fetching of instructions, decoding of instructions, and eventually execution of instructions. Occasionally, there'll be an additional step as part of this sequence, an additional step that involves the storage of processed data, right? So again, the instructions that are in memory, remember the instructions are operating on data, right? But they just don't, the operation or the execution of those instructions when in memory doesn't take place on the memory component, but rather on the CPU. And for that execution process to take place, a sequential process is followed, right? So the instruction is fetched from main memory. It's fetched and taken to the CPU. The CPU will decode the instruction to make sense of what exactly needs to be done. Because you have a fixed set of instructions, you need a mechanism in place for the CPU to know exactly what needs to be done. And so you need to decode that instruction. And then once the instruction is decoded, it is then eventually executed. And usually this execution will almost always result in an output, right? If that output is in the form of data, the data has to be stored back to memory, right? So key ideas associated with von Neumann architecture: single memory component where data and instructions will sit, essentially RAM. And then the data and the instructions are uniquely identified by memory addresses, right? The memory addresses are unique locations. Now obviously you have a finite number of memory addresses, right? And the memory addresses will be dependent on the amount of RAM that you have, right? So, and don't worry if this is a bit confusing right now, eventually it will make sense. We have a dedicated discussion where we look at how we look at this whole notion of memory being contiguous, right? So we look at how these addresses are actually organized, or how memory is actually organized based on addresses. It will make sense eventually. Great. All you have to take note here is just these key ideas associated with the von Neumann architecture, key ideas associated with the stored program concept. Again, very simple idea, but extremely powerful, right? But it turns out really that there are other alternative architectures out there. Now, as this is usually a tradition in 1110, we normally leave it up to the students to do a bit of digging into this very popular alternative that is normally referred to in literature. So the Harvard architecture. I do encourage you to go out there and do a bit of research on what the Harvard architecture is all about and the fundamental differences associated with the fundamental differences between the Harvard architecture and the von Neumann architecture. I'd really love to hear your thoughts on this next week when we do meet, which is Wednesday, I think. Something else I'd want us to do is maybe just to see if we can research additional alternatives besides the Harvard architecture. All right, so in terms of the actual specific architecture associated with the von Neumann model, the high level von Neumann architecture is actually composed of certain key functional units. So those key functional units, actually 4 of them actually. Those 4 functional units is just the input unit, output unit. Sometimes the input output unit will be presented as one because they serve the same function, right? And then you have the central processing unit. So the input unit is the one that's responsible for accepting the imputed data, right? So it could be the component that is responsible to take in sound coming through the microphone. Keyboard, right? The output could be your LCD screen, for instance. And then you have the central processing unit and the memory component. Now, it's usually the case that the central processing unit is further split up into some really important components that comprise the central processing unit. And that's the arithmetic logic unit, which is responsible for performing the very basic arithmetic operations, addition, subtraction, multiplication, and division. And then the control unit, which partially does the decoding of the instruction. It's the one that is responsible to actually make sense out of the instruction that has been fetched, right? Remember we said instructions are fetched, right? And decoded. The decoding of the instructions is actually done by the control unit. And then you have the memory component, which is actually responsible for the storage of data and instructions. Right? Very basic idea here, but very powerful, right? So we will go through these different functional units, von Neumann architecture functional units in sequence, but just to remind us that the von Neumann architecture is essentially composed of 3 high-level functional units. Sometimes you could just say 4 because input and output could be split into 2. So the input and output functional unit, you have the central processing unit, which is fundamentally composed of the control unit and the arithmetic logic unit, although there are other components on the central processing unit itself, like hash, for instance. And then you have the memory unit, which is responsible for the storage of data, right? So input and output is the one that handles input data and output data after it's processed by the central processing unit. The central processing unit is the one that executes the instructions, right? The one that does the processing, otherwise referred to as the brain of the computer, whatever that means. And then the memory component, the one that's responsible for storing program data and instructions, right? But it turns out that there's actually other important components that you can associate to the von Neumann architecture. And some of these important components will come up in subsequent lecture series. Some of them will manifest themselves once we look at these components in succession, right? But I just thought I would mention some other important components right now. So things like the registers. These are small or temporal storage locations that you typically find on the central processing unit, right? And by the way, the whole notion of the computer is centered around certain key things. Key thing associated with the computer system is automation. We use it because we are too lazy to do certain things. Or not too lazy, but we use it because we would want it to perform things that would do at a very slow rate on our behalf, and repetitive tasks also, right? And registers are normally linked to efficiency, so performing certain tasks at a relatively faster rate, right? It turns out, right, that if you solely rely on the memory component when you're fetching data and instructions, it slows down the processing that takes place on the CPU. So to increase the computational power of the computer system, you have these temporal storage locations called registers, right? That will normally hold intermediate results as computations are taking place on the CPU. Again, we provide examples of some classic examples of registers in this lecture series. But I just thought I would make mention of the fact that they're just temporal storage locations. You could think of them as being memory components also, by the way, right? Because what they do is they temporarily store data and instructions, essentially. All right, and then you also have buses, right? Remember, you have these different memory functional units and smaller subcomponents associated with these different functional units here. There has to be a way in which data is transmitted in between, or signals are transmitted in between these different components. And that is facilitated by so-called buses, right? Buses are nothing more than just wires, right? Physical wires that facilitate the transmission of signals, data in between the different components. All right, just putting it all together, essentially, we are saying that partially this whole thing we are calling the von Neumann architecture is supposed to result into something like this. Now, this is just it's showing us a motherboard of, I'm not sure what this board is, but you notice that this motherboard has a number of interesting components like this would be a CPU socket, right, where the CPU typically sit. And then you have slots that facilitates the integration of different input-output components, right? But the thing I wanted to draw attention to essentially is that all these different things that you find on the motherboard are interconnected to each other using buses, right? So this chipset here will typically have small little wires that interconnect the different components that you find on your typical motherboard. All right, so just to recap this first part of the lecture series here, key things that I want everybody to take out of this here is the idea surrounding the stored program concept, the idea of a fixed piece of hardware and fixed set of instructions, and then the von Neumann model, right? High-level functional units associated with the von Neumann model and the basic concepts associated with the von Neumann model. So in the next part of the lecture series, we're just going to go through the high-level functional units and added units here or components associated with von Neumann architecture one at a time so that we gain an appreciation of what their purpose is. All right, I'll see you in the next lecture series. Thanks.